Hello, in today's video, I'm going to show you how to find the exact value of the series 5n squared minus 6n plus 7 all over 4 to the n, where the series goes from 1 to infinity. The goal is by the end of the video is that you'll be able to generalize this for any one of such form. And so what we're going to do is break this problem up into 3 stages in order to be able to generalize it for this kind of question, and then I'm going to show you how to broaden it further for any polynomial over a to the n. And of course, we're assuming that a is greater than 1 because it has to be something that we know is convergent. So the first part we're going to do is establish how to derive the value of the constant term. That is the c over a to the n, where c is just a number. And of course, we all should know this one, but I'm going to run through it real fast. This one is essentially the geometric series. And what we're going to do is establish or identify that initially we could see that c over a to the n would just be the summations of c over a plus c over a squared plus c over a cubed plus c over a to the fourth, and so on, so on, so on. And because we know it converges by the geometric series test, I can say it equals to some value that we call s. And we all know the trick here, just times everything by c over a, in which case you would see that the first term would become c over a squared, then c over a cubed, and c over a fourth, and that would equal 1 over a times s. Take the first series, summation of s, and subtract the second one, and what you end up with is a minus 1 over a times s equals c over a, because that very first term of c over a wouldn't cancel out if we subtracted the two series apart. Now all we got to do is solve for s, and we would know what that first one would equal, that first series of the constant over a to the n. And therefore, the series of c over a to the n would equal c times 1 over a minus 1. I'm going to keep in that form because we're going to see that form pop up multiple times when we do other terms in a bit. So that was the constant term. So the next one we're going to establish now is how to find it for a linear term in the numerator. So in this case, we have c times n, where c is, of course, a constant, and a is greater than 1, and n is just, n. It's one of our numbers that we're using as our terms. And so notice that when we do c over n, cn over a to the n, we end up with the following series: c over a, 2c, plus 2c over a squared, plus 3c over a cubed, plus 4c over a to the fourth, and so on, so on, so on. And it would equal some s, some sum. And we know it equals some sum because if you did the ratio test, you could verify that this thing does in fact converge. So what we're going to do here now, because we know it converges, is bust out the terms and make them everything a unit fraction, where the numerator is 1 essentially. And so if I have c over a and plus 2c over a squared plus 3c over a cubed plus 4c over a4, that means instead of saying 2c over a squared, I can say I have c over a squared plus c over a squared. There's 2 of them. And then I can say there's 3 of the c over a cubes, and then there's 4 of the c over a fourths, and then it would be 5 of the c over a to the fifth, and so forth. And because it's convergent, I can move the order of the terms around and not change the value of anything because we know it adds up to a finite value. And so what I'm going to do is simply take one of each of these terms, 1 over c over a, 1 of the c over a over 2, 1 of the c over a3, 1 over c over a4, and put it at the very front. And then I'm going to do the same thing again for what's left over. And just notice what's left over the next time, it would have to start at c over a squared because there was only 1 over c over a's. And then the third time, if I were to continue this, it would start at c over a cubed. And if I did it again, it would start at c over a to the fourth, and so forth. And so now what I'm doing, though, is I'm creating a bunch of unique groups that I can now put into summation form. And so this very first one should look very familiar. That was our original term of c over a to the n. The next one's almost like that. It's just shifted because there's a 2 here. So instead of saying a to the n, I'd have to say a to the n plus 1 for that 2. In the third case, it's a 3, so a n plus 2, and then, of course, a n plus 3, and so forth. And so what that does, it gives me a bunch of summations that are just a rewrite of everything above it. Now, of course, there's still a lot of sums. I could find each sum independently and find some way to then, compile them from there, but it's a lot of work. So instead, what I'm going to do is try to make them all in the same series format, that c over a to the n, so I can find some way to bring them together. And because c over a to the n plus 1 just means there's an extra a in the denominator, I can pull that out. And the c over a to the n plus 2 would just have two a's in the denominator, so I can pull it out. And then the third one, or fourth one here, a n plus 3, I have to pull out a cubed in the denominator. And then, of course, just repeat that pattern on and on and on, which means I now have 1 over a squared, 1 over a cubed, 1 over a to the fourth, and so forth, by pulling out those a's from the denominator. Now notice in each case, I have the series of c over a n as a term for each of these. So I can factor that thing out. And in doing so, I'm left with 1 plus 1 over a squared, 1 over a cubed, 1 over a4. And just rewriting the 1 so I can see it a little nicer, I can find that there's a nice pattern inside these parentheses. 1 over a0, 1 over a, and so forth. It's essentially c over a to the n, but now shifted to start at 0, which means I just got to write n minus 1 to represent that 0. And I do that on the left here. And again, I want to be able to combine these series up to have the same kind of constant over a to the n. So I can just pull out an a from the denominator, but since the minus 1 is actually in the numerator, and I can slap on an a out front here. And now I have a constant over a n in both places. And now that it's in the form that we originally established, c over a n, I can now use our formula that we originally wrote. And so we have a times this first expression, c over a to the n is just c times 1 over a minus 1, and then times the second expression, which is a constant, it's now a 1, so it's going to be 1 times 1 over a minus 1, or just 1 over a minus 1. And that's exactly what I do on the far left here. Combining everything together, we see it becomes ac over a minus 1 squared. And just for what I want to use later on, I can put it in partial fraction decomposition form and have this wonderful expression on the very far right, which is c times 1 over a minus 1 plus 1 over a minus 1 squared. We're going to use that one much later on. Not yet, but we'll use it later. Okay, we did the constant term and the linear term. Now let's establish a way to find the quadratic term. And then we can actually answer that particular question and then go on and generalize this further. So much like last time, I'm just going to list out all the terms. And so cn squared would become c over a, 4c over a squared, 9c over a cubed. And of course, we're adding these all up. And one thing you can realize, just like before, is I can take one of each of these and put it in my first group because there's one of every term. And that means there's one less for the subsequent terms. And so for this 4c over a squared, there's now only 3 of them. And so starting at c over a squared, we'd have 3 of each of these terms. And since I used 1 and 3, I used 4 total to this point. For the a cubed section, there's 5 left because, 4 minus plus 5 is 9. And then once I used all 9 of those CA cubes up, I only have 7 of the C over A4s left because I used 1 in here, 3, and 5. So I only have 7 left. And so you might be seeing a pattern that goes 1, 3, 5, 7, and then the next one would be 9, and then 11 and 13. And you may also notice it goes a, then a squared, then a cubed, and a fourth. And so each one starts one term up. So that means I can rewrite each of these as a nice summation. The very first one is one of them, and it's c over a n because it's that base format. Then we're starting at a squared, so now it's a to the n plus 1, but there's, of course, 3 of them. A n plus 2 because it starts at 3, and there's 5 of them. A n plus 3 because it starts at 4, and there's 7 of them. And again, the next one would be 9 times the series of c over a n plus 4, and then 11 times the series of c over a n plus 5, and so on. And just like we did previously, what we're going to do is put them all in the same base format of c over a sub n, which means I need to pull out these extra a's in the denominator. So I have 1 here, 2, and 3. So I have 1 over a squared, 1 over a cubed, times those coefficients together, and I get something much nicer to work with now. Now that everybody has the sum of c over a n as a term, I can factor that out, leaving the original 1, which we know is 1 over a to the 0, and then 3 over a, 5 over a squared, 7 over a cubed. And just like before, we now have something we can write as a series. And so a to the 0, a1, a2, a3 is just a n minus 1. The numerator is 1, 3, 5, 7. We see the slope here is 2. And we can see that we need to take away 1 to get each of these values when we start doubling. So we get the series formula of 2n minus 1 over a to the n minus 1. And again, I want this to be some kind of term over a to the n, but we'll get to that in a second. So what I want to do is first make the a n minus 1 fixed. So I just pull out an a, and of course that a is technically in the numerator because it's minus 1, so the a just comes out to the front. And what I'm going to do, so I don't want it right there, I want it in the very far front, I'm going to move the a all the way out. And then I'm going to rewrite this series 2n minus 1 over an into the format we've handled before, which was a linear term over an and a constant term over an. And so there we go. I pulled the a out to the front, and then I broke up the 2n minus 1 to get 2n over an and minus 1 over an. And now that each of those series are in the forms that we know how to evaluate for, we can then generalize our solution in this case. And so recall that when we have a constant over an, it's c times 1 over a minus 1. And when it says cn over a to the n, it becomes the constant c times a over a minus 1 squared. And so our very first one, we still have a out there, but then we have the series of c over a to the n. And that's just going to be a times c of 1 over a minus 1, which is that first one, right? It's just a direct translation. The next one's 2n over an. Notice 2 is our constant, so we just plug 2 into our series. And we end up with this expression, to our formula, I mean. And our third one, notice it's not a c on top, it's actually a minus 1, so you plug in minus 1 for c, and you get that last value. And so if I choose to kind of simplify that down, you can see that it becomes this expression here in the middle, 2a squared c over a minus 1 cubed, minus ac over a minus 1 squared, or the much nicer partial fraction decomposition form, which is the one on the far right. And I'm going to use that one just because it's a little cleaner and a little nicer to work with. So now we have all the parts to answer the question. So we have the series from 1 to infinity of 5n squared minus 6n plus 7 all over 4n. And notice we can break it apart to 5n squared over 4n minus the series of 5n squared over 4n minus the series of 6n over 4n plus the series of 7 over 4n, everything going from 1 to infinity. And we have our three facts. One breaks down the quadratic, one breaks down the linear, one breaks down the constant in terms of how the numerator is represented. And so looking at that, the 5n squared piece would just become plugging in 5 for c and recognizing that a minus 1 means you're 4 minus 1. And so you get 5 times the quantity of 1/3, 3 over 3 squared, plus 2 over 3 cubed. Now we have the next term. Notice that our c is 6, so we have minus 6 for c. We're using the second series now. And then 1 over 3 plus 1 over 3 squared. And so boom. And then our very last term, our constant term, we got a c is 7, and of course a is 4, so we get 7 times 1/3. Evaluating that, we get 91 over 27, and if you check Wolfram alpha, you'll see it's the exact same solution. And so there you go, that's how you'd find that exact solution. And you now have these three facts that you can always utilize when you answer anything in the quadratic power form of a geometric series. Now, what if I want to generalize this beyond a quadratic? For those who are interested, continue watching. To do that, we're going to look at two great observations, I think, one for the denominator and one for the numerator, and then we're going to see how to put that together to get our solution. The denominator is usually easier to notice the pattern for, so we're going to start there, then we'll look at the numerator next. And again, this applies for any series where you have a polynomial in the numerator over the geometric term where that a is greater than 1. So what we've established already were those base 3 values. And one thing I want you to notice is when we had a constant term on top, in the denominator we had a minus 1 to the 1 power. So the constant had no n. N was to the 0. The 0 was the degree 0 of the coefficient of the n up there in the numerator. And we end up with the power of 1. In the second case, we have c times n to the 1. And now we go all the way out to a squared power, 2 power. And then the third case, we had n squared. And now notice our denominator goes all the way out to a 3rd power. So what you'll notice is it always goes out to a power higher than whatever the numerator's power is. So had it been c to the n to the 4th, it would have gone all the way out to the 5th power in the denominator. And so if it was like c times n to the 7th, it would be a minus 1, a minus 1 squared, a minus 1 cubed, all the way out to the 7th power. Assuming we're talking about partial fraction decomposition format, the fractions adding up, not in some kind of big, product way. But still a nice format. So whatever power you're dealing with, if it's cn squared, you go out to the 3rd power. If it's cn to the 5th, you go out to the 6th power, and so forth. And that's the denominator format. And just to kind of connect the dots here, notice that we were dealing with 5n squared, and so I went all the way out to the 3rd power. I had 6 to the n, so I went out to the 2nd power for the 6th term, and then 7 was a constant, so I just went out 1 time the power of 1. And so again, you can see that translates right there. Now, ignoring the constant term, ignoring that c each time, I had cn squared, cn, just c, and ignoring the c itself, we can actually evaluate the numerators, which is why when I kept writing those things, I would have c times 1 over a minus 1 and c times 1 over a minus 1 squared. I always had that c factored out because we're going to ignore that c. You can just times it through when you're done. And when you look at these are all the coefficients that you would get on the questions. Like in this case, I had 1, 3, 2, 1, 1, and 1. The very first row is 1, 1, 1, 1, 3, 2. Those are the coefficients that you would get from using this process every single time. Take a second and think and see if you can figure out where these coefficients come from. Anybody who has practiced modeling polynomial functions may recognize these coefficients. That's right, they're actually just the arithmetic common differences. And so, for example, if I did n to the 4th here, so I did 1 to the 4th power is 1, 2 to the 4th power is 16, 3 to the 4th power is 81. And then all I did was find the common differences for each one. So 16 take away 1, 81 take away 16, 256 take away 81, all the adjacent differences. Of course, I would get those values. And then if I keep subtracting on and on and on until I get a row where all the differences are the same, they're all commonly the same difference. That's why it's called common differences. I would eventually get to a point where they're all 24s in this case. And what you'll notice is that very first column, those were the numerators to our fractions. And so if you find your common differences, you actually get your numerators to those fractions. And maybe in another video, I'll show you why this works. But those are essentially what you're getting. Those become your values and they go in ascending order. So this 1 goes over a minus 1. 15 goes over a minus 1 squared. 50 goes over a minus 1 cubed. 60 goes over a minus 1 to the 4th power, and so forth. And so those values, once you get to your row of common differences, become your numerator. And again, just to connect it, see we had 1, 15, 50, 60, 24, 1, 15, 50, 60, 24. Those are where the values come from. So now let's put it all together. Let's say we actually want to do this problem, 6n to the 6 over 3n. Looking at the denominator, we notice the 3. So 3 minus 1 is 2. So all the denominators are in base 2. And this is a power of 6 on top. So it starts at 2 to the 1, 2 to the 2, 2 to the 3, etc., all the way to 2 to the 7th. And then our numerators, if I make a chart, ignoring the 6, of course, ignoring that constant, I can make a chart and quickly find that row where all the differences are common. And now I have my numerators, 163, 602, 2100, and so forth. And so putting those two facts together, I get essentially 1 over 2, 63 over 2 squared, 602 over 2 cubed, 2100 over 2 to the 4th, and so forth. Give me all those fractions. And of course, we know we got to remember the times by that constant 6. And when you do, you get 4473 over 2, which is the exact same value you would get by utilizing Wolfram alpha. But you can now do an exact calculation. And I would think in most cases, that first half of it would be all you would have to do because the rest is just using a calculator. If you're using a calculator anyways, then, you don't need to do it by hand, right? Okay, well, that will hopefully help show you at least how to start doing these problems in terms of generalizing them for anyone in the form of a polynomial over a geometric series where the geometric term is greater than 1 when it's in the denominator. All right, everybody, this is my first video, so I hope it was helpful and beneficial and all that. Thanks for watching and have a great day.